So to the presenter, you have 20 minutes and you will be informed of the time at the 15-minute mark. You now have the floor and good luck.
All right. So can I share my screen now?
Yeah.
Okay. And am I audible clearly?
Yes, we can hear you.
Okay. Yeah. Thank you. Good afternoon, everyone. My name is Kiran Bodipati, and I'd like to present my paper, Explainability of Deep Learning-Based Graph Embeddings. Before I talk to you about this, let us first discuss what explainable AI is and why it's important. Most machine learning models we see today are black box in nature. This means that the model does give a good result, but we're not able to understand why the models provide such results. Explainable AI is the AI which humans can naturally understand and explain by observation and simple reasoning based on the observations. It's important to understand why any model works the way it works, because it helps us create better models and make better use of the AI that we have. Okay, now coming to graph networks. Graph data structures are one of the most common data structures that we see in real life scenarios, be it for social media networks and connections, study of road networks, study of chemical and biological proteins. Almost each and every real life scenario uses graphs for its representation. In fact, the study of the spread of COVID-19 and the subsequent contact tracing of the cases is also done with the help of graph networks. However, there are a few issues that we encounter when we are working with graph data structures. First is that the meaning of nodes and edges generally change from graph to graph. They are not constant. Further, the dimensionality and size of the graph is potentially infinite, and even in most real cases, the size of graph is so large that it becomes almost impossible for heuristic or predetermined algorithms to handle the graphs. Third, the same graph can be represented in many different ways. This problem is generally known as the graph isomorphism problem that we commonly study. All these problems together make it hard for heuristic algorithms to deal with graph data. All right. So to tackle this drawback, graph convolutional networks have been created. They help in better capturing of the node features and the edge features due to the convolutional nature of the networks, and provide state-of-the-art results for the node classification problem as well as the graph classification problem. Although for our study, we focus only on the node classification problem, it is very interesting to note that graph convolutional networks indeed provide state-of-the-art results for tasks such as text classification and image classification too. These are tasks that traditionally use CNNs and RNNs for its performance, and yet you have graph networks that actually perform well on them. Despite the fact that GNNs provide very good results, they're highly black box in nature. This is because graph embeddings lack ordered vector representations and lack symmetry, unlike the word vector embeddings and image embeddings. Further, as mentioned earlier, the graphs are arbitrary in nature, and all these make it difficult for humans to explain the results that is generated by the graph neural networks. There are various advantages in being able to gain a better understanding of the GNNs. First, it makes the model more transparent, and we can trust the model more. This, in turn, helps improve the model in terms of its performance, privacy, and fairness. Next, it provides an insight into the patterns and characteristics of the network, which can in turn provide a better understanding of the graph data that is operated by the network. Hence, it's essential that we understand the underlying intricacies involved to provide suitable explanations. There have been numerous studies, of course, attempting to provide an explanation to the graph embedding generated by a deep learning model to understand what aspects of input data may affect the predictions provided by the GNNs.
Ask any. Huh?
Okay. Sorry. Yeah. However, although there have been numerous studies, there's no one correct answer, and you have multiple ways of explaining this. Hence, in this study, I focus on gaining insights into the node classification problem and provide a post hoc explanation to the embeddings generated for a node by studying the features of the neighboring nodes of a given node. Before we look at the results of the study, let us take a look into the previous work that was done in the interpretability of neural network-based graph embeddings. So the study into the interpretability of graph networks can be mainly divided into two categories. First is the intrinsic method, where the deep learning model itself contains mechanisms to provide an explanation. The other is a post hoc or extrinsic method, where an external interpretability model is developed to generate explanations. Sometimes the interpretability models are specific for a given neural network, and sometimes they can be general, which I will discuss further. The global intrinsic interpretability methods use rule-based decision trees and forests to provide their explanations. At the node level, we also have the graph attention mechanism, which provides an intrinsic explanation. On the other hand, there are post hoc methods that employ external models to provide these explanations. At the class level, some methods include the permutation feature importance and the activation mechanism. The node level explainability methods include the occultation based models as well as the backpropagation based models. In this study, since I've used both the post hoc node level techniques, let me explain them in more detail. The backpropagation includes techniques like the GradCam and deep lift approaches. In the backpropagation model, the importance features are propagated from the output neuron layer to the input layer. In specific, the GradCam approach uses a gradient descent based approach to propagate this importance feature. Post-hoc interpretability, the occultation-based interpretability models are post-hoc interpretability models that try to understand the classification by studying the node features and its surroundings. These models generally provide independence over the deep learning models that is used to generate the embeddings and can be used for any sort of embedding that's generated. While the study into occultation-based models are limited, there are two techniques. There are two techniques that are used. That is the GNN explainer and the groupin. The groupin tries to cluster the nodes first and then provide the most important features for a particular node. On the other hand, GNN explainer first tries to find a subgraph for the nodes that play the most important role in obtaining the results and then provides the explanation. For example, let us take a particular node Vi, as you can see over here. This node represents the feature called basketball. And the image here represents the vicinity around that node. The GNN explainer tries to find the feature that provide the most important role in trying to classify this node as basketball. As you can see from the explanation provided over here, features such as throw ball, volleyball, football, baseball, etc., play an important role in classifying the node Vi as basketball, while features such as running and cycling do not play important roles. Hence, those are not included in the subgraph. Okay, now that we've gained insights into the background research, let us move on to seeing the scope of this study and the experimental setup that I've used. So in the study, I focused on the node classification task, and I used a comparison of two interpretability models. One was the backpropagation-based model, that is the GradCam, and the other was the occlusion-based model, that is the GNN explainer. Both of these have been briefed to you just earlier. Now, by studying the node features with respect to the neighboring nodes, I try to provide a qualitative analysis of the interpretations generated for the nodes of a specific class. For this study, 4 data sets were used. One is a house-shaped graph. Another is a random community shape graph. The third is a grid. And the third is a tree grid. And fourth is a tree cycle. All of these are synthetic data sets, and they contain 4, 8, 2, and 2 classes in each of them respectively. A graph convolutional network was used to classify the nodes and generate a d-dimensional embedding for each of the classes. For a given embedding, the node feature values of a class are studied and compared across those of another class, and we make use of interpretability models for this. Okay, so this is the experimental flow that I just described to you earlier in a pictorial way. Let me pause for a minute while you can take a look at this. All right. So and now that we've gained an insight into the experimental flow, let us take a look at the results that I obtained and the insights that we can draw from them. First, we have a qualitative study that focuses on the accuracy of the interpretability model. The problem of interpretation is generalized as a binary classification, where the ground truth acts as a reference and the edges are considered to be labels. The data obtained from the explanation models, that is, the information of the importance features, is treated as a prediction. If the ground truth of the edges are close enough to the predictions offered by the explainer is said to be accurate. From this table, you can see that for each of the synthetic data sets I've used, the GNN explainer outperforms the accuracy of the GradCam by almost like 4 to 10% in some of the cases. The lowest score of the GradCam can be attributed to any inaccuracies that may have arisen from the gradient saturation, because this follows the gradient-based approach. While my research did not focus on the time complexity of the two models that I used, there have been other studies that have shown that GradCam is efficient in terms of the time taken to generate an explanation, which becomes very, very useful when trying to generate interpretations for very large graph data sets, for example, the road network data sets. So it's basically a trade-off between the accuracy and the time complexity of the model. So it depends upon the situation. If you need a more accurate model, you go for an accurate model. And if you need a model that gives you faster results, then you go for a model which has like lesser accuracy but a faster time processing. Next is the qualitative study of this data. So, for a given data set, by studying the neighboring nodes, we were able to obtain the mass density as well as the predicted node feature tensors that were predicted by the two interpretability models, that is, the GNN explainer and the GradCam models. These were compared for the nodes across different classes. We then generated adjacency heat maps and the subgraphs for the important features of the same. For this example result that I used in this slide, I used a tree-grid data set, which is a two-class data set, and a 10-dimensional embedding, and I've generated the explanations with the help of a GNN explainer. Here you have nodes 400 and nodes 500 in a class called 0, and you have nodes 512 and nodes 600 in a class called 1. As you can see, the predicted tensors that are across the same class are very, very similar. If you can see for node 400 and 500, they're almost the same. And for nodes 512 and nodes 600, they're very, very close by. But they're slightly, but they're different from that of nodes 400 and 500. Similarly, if you observe the mass density, then again, within the same class, you have similar results, while for that of a different class, you have different results. Next, if you observe the patterns of the adjacency heat maps generated by the GNN explainer for the respective nodes in the figure over here, we see that the heat maps of the nodes of the same class again follow a similar pattern. That is, nodes 400 and 500 have a similar structure, while nodes 512 and node 600 again have another similar structure, and this varies slightly from that of nodes 400 and 600. Similarly, if we observe the subgraph that was generated, you again see similar features. If you can see node 400 and node 500, they have a disconnected subgraph, while nodes 500 and nodes 512 and node 600, which belong to class 1, have similar structures. They have more of these diamond-based connected structures. So they have similar features for within the same class, and they differ from that of a different class. Um, Now, this figure provides a comparison between the important node neighbors that have been generated by the two different interpretability models. One is the GradCam and one is the GNN explainer. Although they look different, both of them are like both of them are like correct. There's no one correct way of explaining them, and both of them follow their own approaches. However, if you look at the results that we obtained before, both the models conclude the same. They provide like different values, of course, but then they show a similar trend. So yeah, I think that comes to the end of my results, and I think this is a lot to sink in. So let me wrap things up by providing a quick summary. So given the applications of graph datasets and graph structures in numerous aspects of the world, including road networks and all the other things that I mentioned earlier, the study of the explainability of graph networks is an interesting area of research. My study focused on node classification tasks by representing the nodes in terms of its neighboring features. Post-hoc interpretability model, that is the GNN explainer, was used to generate the explanations of a graph convolutional network. The data obtained seemed to suggest that for a given d-dimensional vector embedding, the neighboring features played an important role in classifying a node to their respective classes. We observed in the heat maps and subgraphs that the nodes which were clustered into the same class had very similar neighboring features. However, this is a very preliminary observation, and as seen from other previous studies, there is no one correct interpretability method. Hence, the future research can focus on providing a more rigorous mathematical proof to the concepts that I have discussed in my paper. Also, I'd like to acknowledge the funding support from the NTU Eureka undergraduate research program for this research project. And these are some of the references that I have used. So with that, I've come to the end of my presentation. Thank you. Yeah, if any of you have any questions, feel free to ask them.
Thank you to our presenter, Kiran Bodipati. The floor is now open to questions from the audience. So if anyone has any questions, please type them into the Zoom chat and the presenter will address them.
She'll talk 1 hour. The next guest speaker is in half an hour. So I told you.
Hi Leon, and thank you so much for your question. So yeah, the real world applications, right? So as I mentioned earlier, the graphs for networks are used for a variety of tasks, including like COVID contact tracing, etc. And it becomes imperative that we understand the model to actually provide to make our model perform better. We need to fine tune the model. If we have to fine tune the model for any particular task, then we'll actually have to, understand the underlying intricacies and why the particular classification is occurring. So that's why gaining insights into how the behavior of nodes can help in the better pre-processing of the graphs and graph data structures, and it can in turn produce like better results for any of the classification tasks that you have for any of your graph models. So I think that's one interesting application of that. Did I answer your question, or do you need any more clarifications? Okay, yeah, thank you. Anyone else?
So we have a question that says, do you see any scope for improvement in your project right now?
Okay, yes. Okay, so right now, my paper just provided a preliminary analysis, and we need a more conclusive, more rigorous mathematical proof that can cover a lot of general cases, because right now I've used synthetic data sets, and we need to translate these results into the real world data sets itself, and that takes a lot of effort. Further, like, you have a lot of variations within the same research. In fact, I'm working on another research right now where I try to observe the node values with respect to the dimensions. Right now, we kept the dimensionality as a constant, but if you vary the dimensionality of the graphs, I'd like to observe how these results change. So you have a lot of experiments that you can do by changing a few parameters here and there, and it's a really, really interesting field of research, by the way.
If no one has any further questions, the floor is now closed to questions from the audience. I would like to thank our presenter, Kiran Bodipati. I would also like to thank our audience for attending and for participating. So up next, we have two student presentations entitled Personalized Federated Learning, a Combinational Approach, and High Entropy Neural Networks for Reinforcement Learning. These will start at 2 p.m. But before that, we have a guest presentation by Dr. Bo Lee, which is taking place now. So to listen to these, please proceed to the respective Zoom rooms. Thank you for attending.